All right, guys, this is pre-calculus 3.2.3, and we're going to be talking about the area under a curve again. So we've gone over summations and how we can kind of use those. We've kind of estimated how we can find the area by kind of adding up a bunch of different boxes. We're going to kind of put those two things together and take a look at stuff that looks like this. So we're going to start off with a fairly basic equation here. So just f of x is equal to x to the second. So a parabola you've been working with for multiple years now, right? We're only going to look at it when it's on the positive side, and we're specifically only going to look for the area between 1 and 3. Okay, so we see here on this picture, let me see my cursor, we've drawn little rectangles to kind of estimate the area that is underneath that curve. This is effectively kind of similar to what you probably did last time when you kind of had that picture and said, well, if I count up these little boxes, I can get a good estimate, but that's a little bit of an underestimate, right? So this is going to be a good estimate, but we know it's going to be under because we have these little white gaps here, which is saying, hey, I'm not counting that gap, that gap, that gap, or this gap here. And those are going to be sizable amounts. But this is going to be our kind of first step. We're going to find better and better ways of doing this. And by the end, we're going to have a very, very good way to find the area underneath this particular curve. So go ahead and draw this picture out just so that you have something to kind of draw on, right? And so then let's talk about what some of these things mean. So in terms of the rectangle drawn, what does the y value of each coordinate represent? So either coordinate here, 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 and here. So those four are important coordinates for us. So the y values are just going to be the heights of the rectangles, because that's in terms of the rectangle, that's just the height of it, right? And then what's the width of the rectangle? Well, for each one of these, it's the same. It's 0.5, right? I have a width of 0.5, and then my y value, or my height, is changing based off of the actual equation, my x to the second equation, right? So let's harken back to that subscript notation we kind of mentioned when we were doing the different summations, right? We use that to kind of say, well, here's my x sub 0, my x sub 1, my x sub 2, x sub 3, x sub 4, and so forth. This is my kind of first term, second term, sorry, my 0th term, first term, second term, third term, and fourth term, and so forth. We use the x there and then the subscript because these are actually x values that we're going to be using. Because if I call 1 here my 0th term, it's an x value, but it's my 0th x value. My next one is going to be 1.5. That's my first x value. Then my 2 is my second x value. My 2.5 is my third x value. So this is where it gets a little bit confusing for us, purely because I'm calling 1 my 0th, and I'm calling 1.5 my first. And so once you kind of get past how that sounds weird to your brain as far as just plain old English goes, it's not too bad. So this thing, hey, it's my 0th term, then my first term, second. We typically start with like 0. You can start with like 1, but it's just a little bit easier if you do 0. So now the 4 shaded rectangles in the diagram are called left endpoint rectangles. Okay, why are they called left endpoint rectangles? So think back to when we kind of first did the left endpoint and right endpoint stuff with the summations, right? The segment 1 to 1.5, right? The left endpoint of that is on 1. The segment 1.5 to 2, the left endpoint there is 1.5. Segment 2 to 2.5, the left endpoint there is on 2. So all of those are where we're actually hitting the side of the graph. So I'm hitting these on the left side of every single rectangle, hence them being called left endpoint rectangles. Okay, so you can probably make a pretty good guess as to what a right endpoint rectangle would look like, right? As opposed to hitting on the left-hand side, we would just hit them on the right. So this first rectangle would be slid up so that it touches here and goes over in that side. Okay, so that would be a right endpoint rectangle, and spoilers, that's what we're going to end up doing next. So let's see if we can approximate the area under the curve by writing an equivalent sum the total of all of the shaded regions. Okay, write the sum greater than or less than, is it greater than or equal greater than or less than the total area of the actual area under the curve. I'm sorry why I'm not sure why I had a hard time saying that, but I did. So so this width is 0.5. Its height is 1, so I can, well, it's 0.5 times 1, right? And then this width is 0.5. Its height is, if I plug in 1.5 into x to the second, I can figure that out, right? So I'm going to take us to a different screen, and we're going to write that out. So if we do, pull this out. So we said the first one is 0.5 times 1 squared, right? Then our second one is 0.5 times 1.5 squared. Oops, you can't see that. There we go. And then my third one is 0.5 times 2 squared. And my last one is 0.5 times 2.5 squared, right? So if I add all of those up, I believe you get 6.75, if I remember correctly. So we'll do, that's just going to be 0.5 plus 0.5 times 1.5 squared plus 0.5 times 4 plus 0.5 times 2.5 squared. You get 6.75, right? So pretty easy. We just added all of those up and we're done. So hopefully you already kind of see a little bit of why we're doing this now, because there's a shortcut which we could do. This seems eerily similar to what we were doing when we were doing the summation notation, right? We're adding up the same thing, but we're just jumping up by little parts. But we're not jumping up by whole numbers, we're jumping up by fractions here. So how could we shortcut this, right? That's where we're ultimately going to be going. But we're not going to get there quite yet, but we're going to get there eventually. So say look at 115. So what I want you to do is go ahead and pause the video, try this out. It's going to be doing the exact same thing we just did, but now with right endpoint rectangles. So go ahead and pause and try it out. Okay, so a few things which we notice that are a little bit different. So again, our y is still our height, and then our widths are still 0.5. Not a big deal here. And then if we label these, we've got 0, 1, 2, 3, and 4. So the terms which we're actually going to be using are x sub 1, x sub 2, x sub 3, and x sub 4 this time, as opposed to 0 through 3 on the left end points there. Okay, so they're called right end points because, again, I'm hitting on the right corner of all of these rectangles now. Now let's approximate the area underneath the curve here. Now you probably noticed there's a shortcut, just like you noticed that same shortcut when we did these summations, right? Basically, I can just reuse these ones here, because these latter three on my left end point are the former three on my right end point. So all I'm really doing is changing out my bottom one for the top one. So it's going to be that plus 0.5 times 3 squared. So let's try all that. So if we do those, I can really just subtract the 0.5, but I'll do it the proper way. 0.5 times 1.5 squared plus 0.5 times 4 plus 0.5 times 2.5 squared plus 0.5 times 9. 9. We get 10.75, right? So the area underneath the curve there was 10.75. Now that's going to be an overestimate, right? Because here I clearly am always above my actual curve. So 10.75 is bigger than the actual area. My 6.75 for the left end endpoints, that was going to be clearly less than the area, right? So I know now that the actual area is bigger than 6.75, but it's smaller than 10.75. I have to be in that range there. So question becomes, well, how could I get a better estimate? And if you thought about what you did last time, you were trying to kind of estimate the area there, the smaller the piece you ended up using, the more accurate we would be, right? If I changed all of these rectangles and made them half the size, I would have less of that kind of extra bit, right? Same thing if I go back here, if I make these half the size, I'm going to have less of this extra little white area, which is going to be my underestimate. So how can we do that? Well, let's give it a shot. Okay, so go ahead and pause, try out 116 and 117, and then come back and we will go through those together. All right, so 116. Right, so we're still looking at x to the second for 1 through 3, and that gave us an underestimate with the left end points and an overestimate with the right end points. So on A, is it increasing or decreasing between 1 and 3? Well, we're increasing, right? Let's sketch an example of a curve where the right endpoint rectangles will produce an underestimate. So graphically there, if I have any kind of curve that is decreasing, a right endpoint is what's going to give me the underestimate, right? Because then I'm going to be leaving my gaps there. So if I'm decreasing, a right endpoint gives me an underestimate, but then a left endpoint, if I do that in a different color, a left endpoint would be overestimating. Right? So if the ones we've done thus far have been increasing, so that's why the left endpoint was always under and the right was always over. But if I'm decreasing, my right is always under, my left is always over. Now, what if I have a curve which has both, like a sine curve, right? I'm going to get a mixture of over and underestimates depending on where I am on that particular graph. Okay. So. All right, so we already kind of talked about how we can get those closer together if we make those pieces smaller and smaller and smaller and smaller and smaller. Another way which you can do is actually use the midpoint. So you'd actually draw your rectangle so that the middle of your rectangle hits here. So you get something that looks like that, and I'll draw it here. It looks like this. So you get kind of a balance of over and under. But again, there is better ways, which we'll get to eventually, so we really don't need to worry about that all that much. All right, here we go. So 117. So we're going to do that same graph, the same interval, but now we're going to make our rectangles more narrow. So over here, I now have four rectangles between 1 and 2. So the width is now 0.25. Okay. So if the width is 0.25, the height is still based off of the x to the second, right? So that's what I got to plug in. How are the heights generated from the function? Again, we plug them into the equation here. We plug the x value in there. And then let's compute this and see how our answer compares, right? So here, if I do this, there we go, sorry. I would have, well, 0.25 is my width now, not 0.5, right? So 0.25 times 1 squared plus 0.25 times 1.25 squared plus 0.25 times 1.5 squared plus 0.25 times 2 squared plus 0.25 times 2.25 squared plus 0.25 times 2.5 squared plus 0.25 times 2.75. Did I miss some? Yeah, I missed a 1.75 squared into 2.5, 2.75 squared plus 0.25 times 3 squared plus 0.25 times 3.25. Oh, sorry, I need to stop there. I went too far. Okay, I just got on a roll. So I got all those. I got my 1, 2, 3, 4, 5, 6, 7, 8 rectangles that I'm going to have to add up to estimate that. So if we do all of that, 1 second, you should end up getting 7.6875, just to kind of save you from having to type all of that in. So you should get 7.6875. Okay. So that, again, is closer than that 6.75 to 10.75. So now I know, hey, this is even a better bet, but hey, this is still an underestimate, right? I'm still under when I'm using this. So now I know, hey, it's bigger than 7.6875 and less than that 10.75. And I could do the same thing with the right endpoint rectangles and get a lower upper end, and I can eventually kind of make those narrower and narrower and narrower until I get such a small gap that I know effectively exactly where that is going to be. And that's effectively the process we're trying to go through here. So you can probably see where we're going next. I've mentioned these summations quite a bit. Our next job is to say, well, how can we take a summation and do this a whole lot easier? Because as you saw, if I'm adding up a whole bunch of things that are just increasing a little bit each time, that's what summations are for. So our next job is to figure out, hey, how can I write a summation that will find all of this area stuff here? Because the thing that sucks about having so many of those little rectangles is if I want to make my graph more accurate, I need tons and tons of rectangles, right? I had 8 there, and I got even better. What if I did 20? Well, that's better, but do I really want to do 20 addition things by hand? Not really. Well, what if I wanted to do 100 rectangles, right? Even better. But then again, I'm going to have to do 100 of those by hand. So that's why a summation is so nice, because your calculator can do those crazy easy, and then you're done, right? I can make it 10,000. Type it into my calculator, and it'll add up all 10,000 of those rectangles, and it's be really close, and I don't have to do that by hand. So that's effectively where we're kind of going here. All right. So for our closure here, I just want you to kind of think about how well you feel about this. For right now, if you're able to kind of find the areas and add up those rectangles, we're good. Okay. Where we're going to go next is going to be how do we get this into a summation. Okay. So for tonight, there's not going to be any homework, so you don't need to worry about that. If you really want to get a head start, you can. But there might be parts of this section that are going to be easier once we go through the day 2 portion. So with that, I'll talk to you guys next time.